third session of our 3D Thursday webinar series. I'm thrilled to have you all with us today as we dive into the exciting world of additive manufacturing. I, Santosh, will be your host today, and I represent Wipro 3D. As many of you know, additive manufacturing or 3D printing is a revolutionizing various industries. Our topic for this third session is design for additive manufacturing with generative design approach. We will explore the unique of metal additive manufacturing and discuss how evolving designs goals today require innovative solutions like generative design to optimize performance, sustainability, and customization. This session will highlight real world examples from various industrial sectors, showcasing how these technologies are revolutionizing product development. Finally, look at the future potential of metal additive manufacturing and generative design in shaping the next generation of manufacturing. So we encourage a interactive session. So please feel free to ask questions. A dedicated question and answer segment will take place at the end of the presentation, but anytime during the session, you can submit your questions through a chat or a question and answer feature, which you can find it on the UI. To ensure everyone has a chance to participate, we will try to group similar questions together and we will take as many as questions possible and depending on the time which is allotted. Please don't hesitate to ask your questions and also share your thoughts. So lastly, please note that this particular webinar is being recorded. So by participating, consent to the recording being shared for educational purposes. So it's time to introduce our speaker for today. I'm excited to introduce our speaker for today's session, Mr. Vipul Agrawal, a technical specialist from Autodesk Fusion. Vipul, a master degree graduate in manufacturing technology from IIT Bombay, is committed to advancing the manufacturing sector through technological innovation. He began his career as an application engineer, tackling challenges in CAM programming and enhancing productivity on the shop floor. His expertise spans several industries, including medical, automotive, aerospace, and oil and gas. Currently, Vipul works as a technical specialist at Autodesk, so leveraging Autodesk Fusion's integrated CAD, CAM, CAE tools to address industry-specific issues. He collaborates closely with clients to evaluate their design and manufacturing workflows, proposing optimal technology solutions to meet their operational challenges. So let's welcome Mr. Vipul Agarwal as he takes us through today's presentation. Over to you, Mr. Vipul Agarwal.
Thank you, Santosh. So, a welcome to all of you from my side as well. And as Santosh introduced me, I am the technical specialist from Autodesk and I handle Fusion as a product. And today we are here to talk more about design for additive manufacturing. You can think of it as design for manufacturing as well, but very specific to additive requirements. And there has been various developments that has happened in additive manufacturing for which we need to think above and beyond our designing process that we do today. And that is where the generative design approach comes through. We'll deep dive through all of these in the next few slides, which I have. But to start with, a small introduction of myself. So I am in Autodesk from last 5 years. I am based out of Bangalore in India, and I have almost a decade of experience in manufacturing technology. I really like to work with new technologies, so I always will be found to get my hands dirty or my laptop crashed wherever new technologies are there, right? In Autodesk, I handle Fusion as my product portfolio. So it's a complete CAD, CAM, CAE, and MES platform which Autodesk has built, which is again a new age technology platform. And as Santosh told, I have a master's degree from IIT Bombay, and I studied 2 years in Bombay, so I really like that place as well. Now, the story of additive manufacturing in my life starts from that place itself, IIT Bombay. When we were studying several new technologies in there, there was a news that suddenly came up, uh, that we read, was that GE Aerospace has been producing a fuel nozzle, and they are producing it completely with additive manufacturing. It was obviously not a sudden news for them, but it was a sudden news for us because we took additive at that time, and this I'm talking 10 years back, 10, 12 years back, at a very sideline technology where it was just to study it, right? But then a company like G investing and making a actual real part out of it and using it in their mainstream process was something very astonishing. And what have they achieved from this was truly marvelous. So uh, if you have not read about it, it made the complete part lighter by 25%. The design was made simple. It reduced the number of components from 18 to 1. And imagine, like in aerospace industry, it is reducing from 18 to 1. That is like lesser moving parts and lesser complication. And then due to this new technology, manufacturing technology, they had they were able to introduce new design features that were not possible because of the older technologies. And these were the mainstream benefits that they got. But apart from that, because of this, other problematic things like 95% inventory reduction was there, 80% development time savings were there. There were no nuts, bolts, welds, or braces in the design, and that design was made more sturdy according to that. So there were the main benefits, and then there were the second main benefits which were there, which gave it a very cutting edge technology. And then that is where the industry started thinking about generative design. Industry started thinking about additive manufacturing, right? And there was at that time, I believe, in the mainstream, the fourth manufacturing process was added as a common manufacturing process. So we might have heard about every one of you might have heard about all the other three. The casting process, which we say it's kind of an additive process also, but it's just pouring molten metal into a mold. The forging process, which is the zero or neutral process, as we call it, which is which is just shaping the metal out of what you have. And then the machining process actually, which is the subtractive process, which takes out the material from the regular block. And then the additive process, the new age additive process, where we settle the material layer by layer, right? And why was this becoming more and more aggressive and more famous in the industry? And this is because of these five reasons which has been mentioned here. One was sustainability. Since you are not removing material, you're adding up the material, you're using approximately the same type, the equivalent material which is there, and not wasting anything. This was again a sustainable move, and it was very much beneficial from the industry. Shorter production lead times were there, the material usage was reduced, and the spare parts were reduced also. The performance of the parts were able to improve because now they could implement the designs in such a way that the new features, the new functionalities which were not previously possible can be now manufactured. And then it was decentralizing the manufacturing from silos to the whole world. Like the manufacturing machines were the new age machines which were coming up in every industry. Now, apart from this, if we look at the design benefits, if we look at the designer side of benefits of it, the designer was specifically able to produce more complex geometries, right? That would improve the part performance. They were able to make simpler components together. So they were able to make simple geometries which were combined together and not made in different parts. Right. Again, the weight of these geometries was really low. They were fully customizable, and parts could be produced with minimal extra material or minimal extra efforts needed, like no tooling is needed, no fixturing is needed, and those type of thing. And the other thing was you can do rapid iterations on it. These were the key benefits from the designer's perspective that they were getting, through which they were able to make new and good designs than any time before. And another thing was the era of making additive machines simple also got started, because previously the additive machines were bigger, bulkier, and costlier. While now, if we see, the additive machines have gotten shorter, smaller, desktop based, even some metal machines that you can install it at your homes as well. So this becomes makes right now the right time within this 10 years from when I was introduced to additive manufacturing till now, a very good time to start doing work with additive manufacturing completely. And what does it what is required for doing it? So we saw the benefits and everything, but because of those benefits, because of those things that has changed, there is another new aspect that has come up is the designs are getting complicated. And as far as a designer, while I have the flexibility to design it, I need new type of education, new type of goals, new type of understanding to make these new designs. And that is where the design for manufacturing comes into picture. That once you have selected the process, the manufacturing style, that this is the manufacturing I want to adopt. Now you design for it, and you have to now specifically think on that direction, because that is what is going to get the design into real life afterwards. And when we adopt design for manufacturing, there are again various benefits that we get within it, because it is starting. It is the manufacturing has been thought even before the starting of the design. The quality of the designs gets improved. The cost of getting the designs wrong or redoing it gets really low. So the costs are reduced, the qualities are improved, and due to this, the time to market of your products also increases. Apart from this, you have good collaboration with other team members, even for with manufacturers, because they are now also included in the same value chain from the start itself, and the efficiency of the overall processes increases, right? So that is where the design for importance of design for manufacturing comes into picture. And when we think about design for manufacturing in additive terms, there are basically three types or three styles of designing that comes into picture. One is the standard topology optimization that I think most of you might have used it till now. The second one is lattice structuring, and the third one is generative design. So, in simple terms, topology optimization is getting to know what are the areas of the material where there is no use of any metal to be. So, it does a basic stress test on it. Wherever the areas are where the stress is not acting, you can remove the material from there and optimize the topology. Lattice structuring is something again where you can uh, do a lattice structure for inside of the part, so that it is fully solid from the outside but hollow from the inside, with some kind of structuring or some kind of designing which can sustain the load or load cases which are already there. And then the third one is generative design, which we are going to see in detail. So let's start now discussing on how the generative design would help you to do the goal-based designing for additive manufacturing. But again, till now, I'll repeat what Santosh has told me. If you have any doubts, any questions regarding the concepts or basic, or why we are discussing about generative design and additive manufacturing, you can start putting it in the chat, and we will take it up at the end. So we heard additive, generative a lot right now, but what is it basically? So generative design is nothing but an sorry, generative design is nothing but an design exploration technology. So what it will do is, with the given set of inputs, it will give you CAD designs, and with that CAD designs, as a designer, your job would be to find the right fit for yourself. Now, what are this set of inputs and what are the uh, how are the designs presented? That is what something we'll see. But first of all, let's again take a step back and see how the design processes are done today. So if we go ahead in the design process, it would be something like a few concepts are made, and then these few concepts are validated. In this validation, uh, they check about how the performance of the part would be, how the performance of these concepts would be, how is the manufacturability and everything. And once this is checked and everything is done, validation is done, they go for mass production. But do you see a problem here? The problem here is that, oops, I think, okay, so I think the slides got a little missed, but I'll tell you here itself. So the problem here is that the concepts which are getting developed are very limited, and that the basic reason on in front of us is because there is a limited manpower capability of defining a concept. Now, let's just say if it's a complicated design, something like which you can see on the right hand side, how one designer can design it in how much time? A designer can design it in, let's say, 10 hours, 12 hours or something, and he or she can design only one design in that 10 and 12 hours. But what if there is something which can give you hundreds of design within that 10 to 12 hours, right? And this 10 to 12 hours which the designer has invested will only be given to a design which is like manufacturable by one method, and then made by one material type, right? What if the material changes? What if the manufacturability changes? What do we do about that? So that is where the generative design supports you right in the first iteration phase of the complete product development process. It while you are doing the concepts, it helps you by giving you hundreds of different concepts with the given set of inputs that you have for the product development, and using these hundreds of outputs which are there, as a designer, as an engineer, it becomes your job to go ahead and do the selection of what fits best for you, right? So seeing this, there are basically four areas where it can be generative design can be used. First is to get a design suggestion. Like, I'm very randomly sitting, I need to do a design, and what kind of design that I can take up. Second is part consolidation. So if there are several parts, like we saw in the example of GE nozzle, 18 parts combined to one, and I want a combined part of everything. One of the most important one which is there is the change of manufacturing method. So currently the biggest mistake everybody in 3D printing is doing is using the same part which they used to do subtractive manufacturing or any other type of manufacturing, and just doing the 3D print of it. That is wrong. What you have to do is, with the use of 3D printing, whatever are the good aspects of designing as well, you have to adopt that and then implement it in your design and then do the 3D printing of it. And that's where generative design plays a bigger picture, that if you change the manufacturing method, what it will do is it will give you the design according to what you want to achieve from that, like additive manufacturing, right? So these are the challenges today. Oh, so the slides came up here. So this is what I wanted to show you. What happens is the generative design will help you to iterate a lot of concepts at the main iteration phase itself. And then once this iteration phases are there, you can decide from all the concepts, comparing with your, cost, mass, application, and manufacturing processes, what is the best that you can use. Right, you can use a die casting option where the cost is low but the mass is high, and then either you can use a three-axis option or additive option where the cost is high but the mass is less. Now, if this is something which you want to produce only once, then it's better to go with additive manufacturing because the mass is very less and it is serving the main purpose. But if it's something that you want to produce a lot in good numbers, then you might think of going somewhere in the middle, like three-axis machining. Right. So this is what the real engineer jobs comes in. So that is where generative design helps you out. So what are the inputs that we give to generative design? So the first input that we give to the generative design is what is the performance criteria? What is actually that the component needs to perform? Right. The second one would be how it is fixed. So where is it fixed? What are the places where you want it to be same? You don't want anything to change because it is getting fixed into some other assemblies, right? And then what are my manufacturing options for it? So whatever manufacturing options which we can give will it will consider. So right now we have multiple manufacturing options which are there, but the most famous one is additive manufacturing. The reason behind this is we have been trained for hundreds of years to develop components or design components which can serve for other manufacturing processes. But the concept of additive manufacturing is different, and still it the human needs training for it. And also you have to have that thinking of additive manufacturing beforehand. And that is where it becomes more popular to give a software the algorithm to design for additive manufacturing, and then you just evaluate it. Now let's see how it gets done. So this is a quick video on how it would get done. So considering the bike front end, so this is a motorcycle and this is a correction plate that we have which we want to do change it to additive manufacturing or get generative design give us alternate results. So what do? We do define all the geometries from where it is getting connected to other geometries in the complete assembly. Once we define this, we go to the generative space. In this generative space, we select the geometries and define it as preserved geometries because this is something which we don't want to change at all. This is something which is making this complete component connect with other components and giving us a complete assembly. So we don't want anything to change after this. Once we are done this, all the positions which gets logged gets constrained, and then we give the loading conditions to it. So whatever load is acting on that, that will be defined on this place. Now there are other options for defining these loads also, which is modal frequencies, displacement, global loads, local loads, and even vibrational analysis and buckling analysis. Now comes the important part. How do I want to manufacture it? So here you can see there are two options which are very much useful. One is additive manufacturing, where you can give all the other details of additive manufacturing, and it will give you an additive output plus an unrestricted manufacturing option. So unrestricted manufacturing option would give you a complete organic design where this organic design can be further modified into doing manufacturing through additive. Now, once this is done, I hit solve, it goes to the cloud and starts to solving. While it's solving, it will start displaying all the results which has been completed. And what you can do is you can start your analysis right after it. You can even create or filter out according to visual similarity. You can create a graph plot out of it where you can again filter it out or find out which is the concentrated area where you are interested in. And then all the results which interest you, you can take that out or go ahead and view it inside Fusion itself. Once that is done, you can use the manufacturing options to do the manufacturing. Right. So this is what a complete basic iteration of generative design is. Once my presentation ends, I'll also take you to Fusion and show you a live example also in that. Right. But before that, let's hear about some success stories which has been defined. So there is a company called Penumbra, which is an engineering consultancy company. Now they had a project, they got a project of making this handheld device lighter. Right, so you can see that handheld device, which is the image which is at the top left corner. This was something which they wanted to make lighter. And what happened with this was they used generative design with all the given inputs and all the given conditions, and they were able to get the design, the base design, something which you can see on the second image, and the complete body changed into something which you can see on the bottom left side of the image. Right. Now you'll see such an innovative design serving the same purpose and having the same strength. This could not have been possible if we have used a normal manufacturing method. Now we are doing it lighter, we are doing it faster, and even the product performance have increased a lot from this. So you can see it's 74% stronger, and the handle is very good, lightweight as well. Right? The second one was in personal mobility, and this is an electric mobility vehicle which is there. And you could see the orange portion of the design which is there. This is something which was very intuitive. What they wanted to do was they wanted to reduce the frame weight, and they used generative design, translated a lot of ideas, and then the best idea was selected. They also won the CES Best Innovation Award in 2018. And actually, this product is in production completely. And there are, I believe, hundreds of these vehicles all around the world which people are actually using. You can see it's aesthetically very good looking. It is manufactured by Additive Manufacturing, designed by Generative Design, and serves the purpose totally, right? And it's in, again, a very niche EV segment which is available. Another one was in the industrial equipment manufacturer part. So you can see this is something where they got 60% mass reduction, and the design which is there is yeah, which is the one which you can see on the screen. So they initially were users of Inventor, where they used to design a complete big assembly or complete big platform for different industrial machineries. And they wanted to innovate and reduce the mass of their whole design. And that's what they did. So they transferred the Inventor files into Fusion. In Fusion, they used generative design with the given inputs to get that kind of design out of it, right? Then the next one was done by NASA. There is a unit called Jet Propulsion Laboratory, where they wanted to design a concept lander. And if you can see, each and every part of this concept lander is actually generatively designed. If I'll grab my pen here, if you see this, oops, pen, yeah. If you see this body which is there, this is completely designed by generative design. And then these frames also which are there were actually designed by generative design. They further replaced it with standard components just for the ease of manufacturing. But here you can see that they actually took the liberty to design the complete lander into with generative design and made it through 3D printing. All the other options were also used. So sometimes you can use a mix of it as well. Here is where it gets interesting, right? Now, the next one is with General Motors, and this is a very famous use case. This you can also find in many of the studies published all over the internet. So you see this top image which is there is actually a seat bracket. So whenever you sit in your car, if you tie the seat, this is the place where you let me grab the pen again. Yeah, this is the place where you buckle up the seat. Sorry, seat belt, and this portion is something which is hidden inside your back of your seat because this is not something which is not seeable, but it has its own purpose. And it was a complete unit of 8 components where General Motors decided let's do some research and try to change these things and get something more efficient on it. So they used generative design and additive manufacturing in combination, where they redesigned this entirely and got 40% lighter results and 20% stronger results. And this was the final results that was chosen, which they took into production actually. So something where it is changing the industry totally. This is also something which you might have seen if you have ever traveled into a flight. There is always a partition between the crew members' working area and the seats. And if you have traveled in an international flight, between even the business class, economy class, and between even the bigger economy class, between two economies, that there is a partition area which is there. If you have ever touched that partition areas, it's not completely solid. It has been made by via these kind of frame structures which are there. Now, this is also again was designed by Generative using the additive technology where it gave the complete sections or complete strength points where the strength needs to be added. And once receiving the strength points, all the parts of this uh, you can say connections which were there were standardized. It was further done 3D printed, and then that standard 3D printed sections were fitted exactly at the same points or the locations as it was given output in the additive manufacturing generative option. And once they had this, it became a full-fledged structure of looking standard, but again behaving as same as the previous full solid partition which was there. Right. Now, if anybody might have got a question like how it is different. So people might have used topology optimization earlier, and there is always a question that I also get that how is it different from topology optimization? So let's see how it is. So if you say shape optimization or topology optimization, we always use an analogy like this. So let's just say that you need to go, you are going from point A to point B and transporting some material here in this, and you are taking the red route. What topology optimization or shape optimization will do is it will consider the same shape, the same load and everything, and it will just it will just give you an alternate route of it. Now, it might be not 100% efficient when you do these kind of uh, topology optimization studies. While what generative design does is the main aim is to transport goods from A to B, right? And the second aim here is to transport goods at the less at a very efficient cost or a most less cost from A to B. And that is what it will do. It will try to find out all the alternate routes It can be a ship, it can be a truck, it can be a train, it can be a combination of all of this, where you would be able to transport the goods from A to B in the cheapest form. So that is what generative design is also doing, with the aim in mind that these are the given design inputs to me. It is designing for whatever your main aim is, to get a very efficient and easy design, not just digging out the material from the standard designs, right? So this is basically, yes, it's a related technology, but not as same as the one which is there, generative design. Yeah. A few more, comparison on generative design technologies with topology optimization. One is, for topology optimization requires an expert, while generative design requires only inputs, and then once you have all the outcomes, you just have to take out the best outcome and select the best option which is there. It is typically for lightweight goaling only, the topology optimization. While here, I showed you there are four different ways of looking at it. Maybe change of manufacturability, change of material, consolidating parts, all those things. Uh, Topology optimization only gives you one results, while generative design will give you all the alternate results that are possible for the same given inputs which are there. Topology optimization is not manufacturing aware. All the designs needs to be reworked uh, for making it manufacturable. While in generative design, the manufacturability of the complete design has been taken care of. Right, and I think this is my last slide. So uh, what it is doing right now, it's not a replacement. So somebody might also ask, and again, I get this question a lot, like, do you think generative design will replace the human designer from his desk? And the answer is always no, and it will always be no, because generative design is not a replacement, it's a support, it's a complement to what designers are doing. The final work that the designers are doing cannot be replaced by any process, because that needs very detailed analysis which only a human mind can do. Right, so it's a uh, engineering efficiency design exploration. It's a tool that just documents the situation and all those things. But the main crux here is that it doesn't replaces the designer. It is just complementing the designer to make more efficient designs, or select from a given set of designs the most efficient one for his or her use case, right? And if you are thinking like, if it is a right thing for you or not, and if it is something which you should adopt, then if you have yes, if you are answering yes to any of these questions, like, if you want to improve your product performance, if you want to improve your productivity and in innovation capacity in your engineering, if you want to win more business, if you want to reduce cost or weight, if these are the things, and the answer is yes, then additive manufacturing and generative design is something which we should look upon, because that these are the two technologies which are in great boom and which has a lot more capabilities than we can explore. And if your designs are having load carrying requirements, performance requirements, and potential to be manufactured with different materials and processes, then again, this is something which is which you should consider it. Right. So while before going to the question and answer, I would just like to take you back not back, but I'll take you into the platform and show you. I'll just take another 4 or 5 minutes on this, and then we'll move to question answers. But by that time, I request you again, if you can start posting your question and answers, we can be really efficient on taking up the questions. So consider this robotic arm, right? Now, this robotic arm, all the other units are same as standard, but the gripper is something which we are interested in. So you see, this is the standard gripper which is available inside this robotic arm, and I wanted to change this to a design where I can use additive manufacturing for it. So what we do is within Fusion, I just go to the generative design technology, and these are the inputs that we need to give it to generative. So basically, this yellow portions are the starting designs. Since I already had a design, I gave it as a starting shape so that it can take the design from that, inspiration from that. These are the obstacle geometries because these are the components which are at the back end of it, where we do not want any other material or any other uh, hindrance between these things. And then these are the preserved geometries which we want to connect. So essentially, if you see, it's just a back plate which is there, which gets stick to this obstacle geometry so that we can join it together. And then these are the two ends of the gripper which we want to use to make it, grab things up and pull it out. Once I give this inputs plus my design conditions, so I have different type of loading conditions that can be applied. I have different types of constraints that can be applied. So all these things can be given as a basic input, the design input of it. And then I start giving my requirements to it. So what is the factor of safety that I want to maintain? Should I maximize stiffness with some given mass target? Let's say I want to do it 3 kgs. Do I want it to sustain some vibration? Do I want it to have limited displacement? Do I want a buckling factor included in it? These are the design requirements that I can give, one or combination of all of these. Then what are the manufacturing methods I want to use? Unrestricted for a very organic design, additive for a dedicated additive design, right? And then we have other manufacturing methods available also if you want to test that too. And finally, the study materials, like what are the materials which we want to use. And this materials uses the basic properties of all your mechanical, the basic mechanical properties for a particular material. So we can just go and do the material, add the material over here. Now, once I do this, click on generate, it will go ahead, send this to the cloud and start solving. The results, as soon as they are getting generated, they will start displaying up here. Now, this is something which I kept solved, and you can see there are hundreds of designs which are not, uh, which we're not able to solve, and it shows me everything according to that. I can see, okay, failed, converged, generative models, studies. So I can filter out from these options as well, right? And I can create a detailed view. I can create a scatter plot so that I can, see. If you see here, this is the concentrated area where it is having very less mass, but that is stainless steel. Now this is the area where it is having a mass, a decent amount of mass, and it's a high strength steel. While this blue regions are where the factor of safety is too high. So it doesn't make sense for me to, go ahead and take a component which is having a factor of safety of 30 or a factor of safety of 25. So I can just go from here and select the appropriate design and maybe open it. Once I have the design, I can go ahead and convert it and bring it back into my original assembly, and it would look something like this. I did all the pre-work here, and you see, this is something how the gripper would look like, right? It's again aesthetically very good looking, fits really well, and you can manufacture it by additive manufacturing. Great. So I think I spoke a lot. I'll end up here, and